This is our last lesson in Chapter 6. Lesson 8, we're going to look at graphing radical functions today. A radical function is any function that can be written in the form that looks like this equation here. This is our format, standard form. The a value can't be 0. And for even values of the index, the domain of the radical function is all the real numbers that are greater than or equal to that index. This function can also be known as a square root function. Here's some examples. F of x is the square root of x minus 2. We could say g of x is 2 times the cube root of x minus 3 plus 1. So f of x is a square root function, and g of x is a radical function. For the properties, the parent function for the square root is y equals the square root of x, and the radical function would be y equals the nth root of x. That's the parent function. When you reflect a graph across the x-axis, you need a negative a value, whether it's the square root function or an nth root function, a radical function. When you stretch a graph and the a value is bigger than 1, and when you shrink a graph, your a value is a value between 0 and 1. And finally, when we translate a graph horizontally, that's the h value, and vertically, that's the k value. So that would be y equals x minus h, which would be our radicand, and plus k is outside of the radical. And in the radical equation, so we have an nth root of x minus h, and again, the k value is outside of the radical. So the h and the k are behaving like a vertex of sorts, or like a starting spot. So let's give this a try. We're going to take the square root function, y equals square root of x, that would be the parent graph. And in this example, we want to shift that graph 2 units up. So the square root graph shifted 2 units up. We know that the graph would start at 0, 2, and if you take the square root of 1 and add 2, that puts us at 3. If we go over to the square root of 4, so if x is 4, we got the square root of 4, that's 2, and 2 plus 2 is 4. So we entered 4 in there and got a 4 out. So there's our square root of x plus 2. So our h and k is at 0, 2. It's behaving like that vertex or that starting point in this case. And the parent graph was translated as y equals radical x, and this is translated 2 units up, or shifted 2 units up on the vertical. 2 units up. So that was easy. Let's go on to example 3. In example 3, we are going to use 0 for our square root, and substituting a 0, we get negative 3 for y. If we take the square root of 1 and subtract 3, it's negative 2, and then the square root of 4 and subtract 3, we have negative 1. So one thing I want to point out to you is notice that the y values are going up 1 in each case, but the x values are going right 1 and then right 3. So we have this odd pattern. I believe if we go back to example 2, you can see the same thing. In that instance, we went up 1, we went up 3, and if we substituted a 9 in here, the square root of 9 plus 2 would give us 5. You can see that odd pattern where the y's are going 1 up each time. but the x's are going horizontally in an odd pattern, 1, 3, 5, and so on. Okay, so back to example 2. This is translating the parent 3 units down. So we want to sketch that graph. 0, -3 is that HK value. So HK is 0, -3. And the parent is translated 3 units down. So 0, -3, and then 1 up, 1 right, then 1 up and 3 right, and we're out of graph paper with 0, -3 as our HK value. In example 3, you notice that the argument is x minus 3. What does that do to our function? If you substitute a 3 in for x, the square root of 0 is 0. If you substitute a 4 in for x, we're taking the square root of 1, that's 1. And then I want to produce the square root of 4, so I need to put a 7 in there for x, and the square root of 4 is 2. Here again, the y values go 1 up, but the x values are moving in that odd pattern again. HK, our h value is 3, and our k value, there's no k, so 0 is our k value. 3, 0, 4, 1, and then 7, 2. So used up all the graph paper off the chart. So that translated the parent graph 3 units to the right. So we want to write that what happened to that translation. So we translate the parent 3 units right to the right. You might want to turn off the video and graph example 4 for yourself, and then come back to check that you have the same graph that we have. So I'm substituting -2, -1, 2, and 7 to get the movement on the y values going 1 up in each case, and the odd pattern here 1, and then up right 3, and then right 5. This HK is -2, 0. That looks like we've translated the parent graph 2 units to the left. Translates the parent 2 units left. So come over here, -2, 0, -1, 1, 2, 2, and 7, 3. Oh, I said 2, 2. So -2, 0 is our starting point. Did you get that right? I hope so. Then example 5, we're going to graph a square root function that has several things going on, including an a value of 2, and that's greater than 1. So we have an h and a k. That is -3, -1. And remember, the reason that it's -3 is you're taking the argument x plus 3 under the radicand, and you're solving for that x value, which is -3. So you don't want to confuse the plus sign to think that this is supposed to be positive, because that doesn't work there. Okay, so we've solved for the argument. We know our HK value acts like that vertex point. The A value is 2. That's larger than 1. It's going to stretch the parent graph. That stretch factor is going to change the y values. And we'll see that when we substitute some numbers in for our table. And the H and the K are going to translate the parent 3 units left and 1 unit down. So we want to make a table. And let's start out with a -3. So we've got the square root of 0, and then a -2. That's the square root of 1. And we're multiplying times 2. And then we'll put a 1 in there. That's the square root of 4. 2 times 2 is 4, minus 1. That's 3. And lastly, we'll try 6. So the square root of 9 is 3 times 2. That's 6. And then minus 1 is 5. So here you can see how that A value, we went 2 up on the Y, but we still have the 1 up, 1 right, 3 right, and 5 right on the X. So if you didn't want to make the table here, and you knew the behavior from what we've discovered, we could start off at -3, -1, and we want to go 1 unit right, but 2 units up. So starting out 2 up and 1 right, and then we want to go 2 up and 3 right, and then we want to go 2 up and 5 right. So you could still see how this is behaving somewhat like a slope. And the H and the K gave us our starting point in order to graph that square root or that sideways parabola, so it was. And then our last one in the graphing here is going to be a little bit tricky because we've got a negative A value, and it's a fraction as well. So we've got everything going on there. The A value is negative, so it's going to reflect over the x-axis, but the fraction being between 0 and 1 is going to shrink our graph a little bit by a factor of 1/2. So we're reflecting over the x-axis, and it's also a shrink factor. And then our H and K values are +1 and +4, which is a translation of 1 unit up and 4 units to the right. And 4 units to the right. So that's our starting point at 1 and 4. We can think of that as our starting point. So if we put a 2 into our equation and multiplied by -1/2 after we took the square root and then added 4, we're going to end up with 3.5. If we use 5 for our x value, the square root of 4 times -1/2, and then add 4, we're going to end up at 3. And then 10 would put us at 2.5, and 17 would put us at 2. I know our graph paper doesn't go that far, but here, I just want you to see what's happening with the half. Our y values are going up 1/2 each time, but the x values are going right 1, then right 3, then right 5, and then right 7. But we're beginning at 1, 4. So we want to go down 1/2 and right 1. And then we want to go down 1/2 again and right 3. And then we're off the graph paper, so we don't have much to graph. But 1, 4 was our HK value where we're starting the graph. In example 7, we want to use a calculator, and I'm going to let you know what I used for my settings, and then you might want to turn the video off and set this up on your own. I used my X minimum is going to be 1950, and my X maximum, I set that for 2050, and you'll see why when we read the problem. And this X scale, if you have the TI-84, I set my X scale to go 500 at a time. So X is the number, is the years starting at 1950. Okay? And then for the Y values, we had a Y minimum at 0 and a Y maximum I set at 500,000, so 500,000. And I had the scale for the Y values going up 50,000 people at a time. So if you'll turn the video off and get a graph on your calculator, here's what we're looking at. We want to use this function right here, 75,000 times the cube root of x minus 1950. And all of that is under the radical there. So when you get your graph there, the population is on the y-axis, and the years are on the x-axis. And with that view window, you may have to set your window, but you get some exponential growth that looks something like this. Now, the next thing you want to do is you want to know in what year was the population of Corpus Christi 275,000. So if you'll go back into your calculator and graph 275,000 and zoom in, we're looking for that intersection point. So that intersection point is going to tell us the year that the population reached 275,000. And you can do that by finding the intersection point. And I see 1999 and a little more of the next year. So to answer our question, we would have to consider that little more of the next year would round up to the year 2000. So in the year 2000, Corpus Christi, Texas, population reached 275,000 people. Now, I don't know if that's true or not, but you might want to do a little research to verify that we're close to that. In example 8, we're going to graph a cube root function. And if you know anything about the cube root function, the cube root of x, if y is just the cube root of x, that parent graph passes through 0, 0, 1, 1, and negative 1, 1, but it kind of looks a little bit like an S curve of some sort. So that's our parent function, and we're trying to graph x, the cube root of x minus 2. So the rules still apply. My HK is still 2, 0 because there's no K value. So there's no K, that's 0. And my graph is going to be translated to the right 2 units. So we're translating the parent 2 units to the right. Now I could put a negative 6 in there and take the cube root of negative 8, which would be negative 2. So in our graph, we know that negative 6, negative 2 is on our graph. And then if I used a 1, I could take the cube root of negative 1. That's going to be negative 1. So we know that 1, negative 1 is on our graph. And if we used a 2, that's the cube root of 0, so 2, 0 is on our graph. And if we use 3, the cube root of 1 is 1, so 3, 1 is on our graph. And then lastly, if I used a 10, 10, the cube root of 8, that would be 2. And I see I've made a mistake in my 1, negative 1. This point here belongs over here. So you can see this graph starts here and comes up like that, and then it's going to curve over that way. So the red graph is our function graph, example 8, and the blue graph is the parent graph. In number 9, we have lots going on there. Here I've got an A value, so this is my K value, this is the H value, and negative 1/2 is the A value. So we know the A value is a shrink factor since it's a fraction, and it also reflects because it's a negative number. So we're reflecting over the x-axis, and it's going to shrink the graph vertically. And then the translation, our HK, is going to be negative 3 and positive 1. So that's going to translate our graph 3 units left and 1 unit up. It's going to translate the parent. So our shift, we could say it's a shift 3 units to the left and 1 unit up. Okay? So I started out with negative 4 in our equation, and if you substitute negative 4 and take the cube root, multiply by 1/2, and add 1, you're going to get 1 1/2. And then we already know negative 3, 1 is on our graph. If you substitute negative 2, you'll have 1/2, and then substitute 5, you'll have 0. So your y values are going up 1/2 each time, and your x values are going 1, 1, and then 3. So that's not the same as our square root function. So let's see, we're at negative 4, 1 1/2, negative 3, 1, negative 2 1/2, and we're going to cross over here, so it's going to be a backwards S-shaped curve way over there, and this is our HK value at negative 3, positive 1. Example 10 is our last example, and these kind of problems sometimes show up on the SAT. So we got to factor out an 8 from the radicand, and then we can break that cube root into 2 separate cube roots. So we could say, what's the cube root of 8? And then multiply that answer by the cube root of x plus 4, and then subtract 2. And that way we can use this simplified version as a way to graph the translation in a quicker, faster, easier method. So we already know that the cube root looks like that S curve, and here we have an A factor of 2 now, which is a stretch. This is a vertical stretch. And we also know that our H and our K is going to be negative 4 and negative 2. So that's a movement 4 units to the left and 2 units down. And my table using -5, -4, -3, and +4, you can see that vertical movement on the y values. But here we went up 1 and then 1 and then 7. So our cube root is going to look like -4, -2, and then -3, 0, and -5, -4. So you see that movement of 2 up and 2 up, but then we moved 7 units over to get there. So our graph is going really far like that. Okay? All right, that's the end of Chapter 6, Graphing Radical Functions, Inverse Operations. And I hope you do well on your test.